Hello, everyone, and welcome to the Synthace DOE Masterclass Part 3. My name is Faye Mensah. I'm the Life Science Business Director here at Synthace, and I will be your host for today's session. And if you've attended our first and second installment of the DOE Masterclass, welcome back. And if you're here for the first time, we're very excited to have you and can't wait to share today's session with you as well. So before we start, a couple of housekeeping rules. I just tried to explain the format and also some of the features that will actually get the most out of today's session. So please make sure that your Zoom settings are set to computer audio only. And should you have any technical difficulties, send us a private message. My colleague will be in the chat box and will direct you in the right way at the bottom of your screen. And the webinar is going to be recorded as well and will be emailed to you afterwards and made available on our website to watch on demand, so you can share with your colleagues, friends, whoever you want to. We definitely encourage you to take advantage of this interactive session and ask questions into the Q&A box, which you can see on your bottom. Do not use the chat. It's better if you can use the Q&A box so we can really see all the questions coming in. If you want to comment, feel free to do it in the chat. And we will answer all the questions during the second half of this webinar, but please feel free to add them in at any time during the presentation. So today's session, we will go through how to get started with DOE using a tool called Pcr Simulator. And we go through the process of setting goals, factors, and evaluating the process of DOE methodology that you'll be using. So I'm really excited to introduce our third speaker already, our presenter for today's webinar, Dr. Steve Brown. He is part of Synthace Court of DOE experts. Steve has been a DOE evangelist for the last 10 years, working with dozens of biopharma life sciences companies to really harness the power of design of experiments and transform application discovery. So I don't want to talk a lot. I know Steve has got a lot to tell us and really enlightening discussions that we can have afterwards. So without further ado, I really want to hand over to Steve now. And the floor is yours, Steve.
Thank you very much, Fane, and welcome everyone to this third installment of the DOE Masterclass for Biologists. To briefly continue my introductions, I am a biologist and not a statistician. My early training as an experimentalist taught me to run experiments one factor at a time, where I would keep everything constant apart from one variable in order to understand the biological system of interest. It was during the first part of my career as a fermentation technician that I started to look at other ways of performing experiments. I was running a set of 4 bioreactors, and I would find myself looking at the impact of process set points on biological system, and I wouldn't be able to make any sense of my own experiments. So my interest in the DOE methodology was born out of this frustration and me wanting to make better use of the limited resource I had available. So in discussion at work, a course at UCL for chemical engineers looking at multivariate methods of experimentation was suggested. I attended, and it was from that point I became an evangelist for DOE. As I mentioned, I'm not a statistician, and so I wanted to highlight the importance of the availability and development of statistical software in using the DOE methodology. The software has allowed me as a biologist to explore using DOE to rationally design experiments, for which I'm very grateful. To continue my story, I returned to education and a PhD, giving me the opportunity to explore the use of DOE to evaluate complex biological systems. This was the biological system I was researching. This diagram crudely represents glucose metabolism in Saccharomyces cerevisiae, also known as baker's yeast. And so I wanted to see if the DOE methodology could help me to explore the interaction of 6 genes involved in this last step of ethanol metabolism. And I wanted to see how these interacted under different environmental conditions. So these are the factors that I assessed. You can see here's the genotypes where these genes are either on or deleted. And here's the environmental factors and their associated set points. I then added this information into my statistical software package, and I was given a series of experiments to perform, which I did. Initially, I wanted to gain confidence in the DOE approach, and so I started looking at the raw data. I saw that my results were in agreement with the reported literature, And here you can see the impact of aeration on biomass accretion. This gave me the confidence that DOE was indeed useful. And ultimately, the experimentation I conducted gave me explanatory models for the different measured responses of interest. And this in turn gave me amazing insight into the complexity of this biological system. And then I was really impressed when I focused on the genotype by environment interactions, giving me insight into this system that I couldn't find during my literature reviews. Using DOE, I now had an empirical evidence that the function of the ADH4 protein was to produce ethanol when zinc conditions were limited. As a biologist, I'm a very big fan of using DOE for conducting experiments. Today, I want to show you some pragmatic steps in how to get you started using DOE in your day-to-day research. But before I do, a brief recap on the previous webinars, where Marcus showed us why you should utilize the DOE methodology, and Jar Jar followed, showing what the methodology can do, giving different examples of applications it has helped us with in our research. During the previous webinars, mention of these two great resources were made, and I wanted to highlight them again. This paper demonstrates why you want to do DOE, and I'd recommend you give this to any colleagues that remain unconvinced. And this second bit of recommended reading is the DOE Simplified book. In it, the authors examine the nuts and bolts of DOE as simply as possible using worked examples. And thankfully for myself, they also assume the reader has little to no background in statistics. In the second webinar, we showed different applications that we have used DOE to understand, looking specifically at examples highlighted here in yellow. And the message very much was that DOE can be applied across a wide range of research areas in biology. And along with those examples of applications, we referenced that different strategies and designs can be utilized when using DOE. These are the classical stages of sequential DOE methodology, from screening through to optimization and robustness. When thinking of the variables we include in the experiment, we move along these stages, going from the trivial many that we think may have an impact on our system to understanding the significant few that do have an impact. The strategy and associated DOE designs vary depending on whether you are exploring the system or trying to optimize it. In the webinar, we were shown for each application example, a different DOE design was chosen, going from screening of many factors to then detecting interactions and curvature, then dealing with non-linear landscapes, and finally, using a design to optimize and ensure a robust transfection transduction process. Jar Jar then introduced this DOE process flowchart, and I thought it was a very useful high-level overview. He highlighted that this process is similar to what biologists currently do when conducting their research, with only really steps 2 and 5 differing in how you perform them when using DOE. For DOE, you start with literature reviews and gathering knowledge about the space you are interested in. And then, as a biologist, we would use statistical software to give us a design for the experiment. After you've designed, you go into the lab and run that experiment. Then you collect and structure all the data before creating models, visualizing them, and using your subject matter expertise to draw conclusions. One of the great challenges in engaging with DOE is knowing where to start. And I would like to show you how this process only differs slightly from what you typically do as a biologist. In showing you this, I will hopefully give you the confidence to start running your own experiments using DOE. So let's make a start with step 1 of the DOE process, which is identifying all the experiment variables in your biological system or process that you think may impact it. I'm going to introduce you to a tool to help you do this. But first, let me introduce you to Professor Ishikawa, who was part of the engineering faculty at the University of Tokyo. He was noted for his quality management innovations and best known in DOE circles for his cause and effect diagram, known as an Ishikawa diagram. These cause and effect diagrams help facilitate subject matter experts to assign all causes or variables which could impact a goal that they have in mind. Here we see, split into these headings, there are placeholders to prompt the user to think about the detail associated with each of these broad topics. Let's show you how this is used with an engineering example. We have just detected a defect when manufacturing a product, and we are going to use the Ishikawa diagram to capture all the variables we think may cause that defect. We can ask those who run the process what they think happened, or we can conduct a literature review to understand a bit further. And then we populate our findings in the diagram. And so for this example, we can see under the broad topic of personnel, we've included things such as how the operators were trained, or when thinking about the broad topic of the machine, we include blade wear or the speed of the machine that we think may have impacted this defect. I like to use Ishikawa diagrams as a tool to collect my knowledge on the biological system I'm interested in, and then I use this plan to plan my experiments. I also find it a very collaborative tool where I can get experts to contribute to these cause and effect diagrams, expanding my own knowledge. So now let's go step by step through a biologist example using the Ishikawa diagram as a starting point in performing experimentations using DOE. The first step is to define your research goals. Here, our goal is to understand protein expression in a biological system of interest. We may also have a target in mind associated with this goal. We may want to understand how to maximize the concentration of a specific protein, for instance, or minimize an impurity during purification. Indeed, we may have no target at all, but rather would want to explore what impacts protein expression and in what way. Then we want to choose a response. This is something to measure related to our goal of understanding protein expression. Here, we want to measure the concentration of the protein of interest, as well as the concentration of other proteins that we deem as impurities. Additionally, we also want to see how activity of the protein of interest is affected. And so we can start to think about how our measurements give us insight into our goals. And if we like, we can assign targets for these goals. A good thing to consider when choosing a response such as yield is how noisy the associated measurement is. If there is a large amount of noise in your measurement, you may not be able to discern the impact of a variable that you are interested in. And it's for this reason why it's recommended to use quantitative measures rather than qualitative ones. If at this stage you thought your measurement might be quite noisy, I'd recommend using DOE to understand why. See if you can invest some time to improve your assay. It will help you understand your overall goal better. Next, we want to start identifying all the factors of the experimental variables that may influence our goals. Here we've put some broad topics to start us thinking about our variables, including the genetics and the steps in the process, such as purification. If you like, you can always use the other broad topics from the previous Ishikawa diagram to spark this activity. We then get together with our research team and add all the factors we think that might impact our goal. Current knowledge of your biological system will play a large part in filling this out, but don't forget to experiment. Add things like that elution buffer that you haven't tried out in this context before, if you think it may impact your goals. And so here is our protein expression example diagram. I love these diagrams as a tool to really make you think about your research. It also amazes me how they capture the complexity of what you're trying to achieve. Ishikawa diagrams in combination with DOE provide a framework to systematically think about your research and experiment on complex biological systems. So the Ishikawa tool has captured our broad experiment design space of all the things that we think may impact protein expression. Next up in the process is that we then classify each of these factors. We're going to put our factors from the Ishikawa plot into 3 buckets. Controls that are factors you intend to fix during the experimentation, the nuisance bucket, including factors that vary, but they're either hard to control or you have no control over. And finally, experimental factors or experiment variables, which are the ones that you can control and the ones we want to vary during the experimentation, as we think they impact our goal of understanding protein expression. Controls. These are the factors we choose as set point to maintain during experimentation. When thinking about factors to control, think about how well you can control it. Do you think you can adjust a buffer to hit that set point? If not, you may need to add the factor into the next bucket of nuisance factors. Also, reflect on whether you may be able to invest time or in some equipment to improve control or help measure that factor so that you know it's the same between different iterations of your experiments. And finally, with the control bucket, if you have evidence that a factor may impact your response, then you make it one you intend to vary. So we have done that for our protein expression example, and these are the factors that are involved in the experiment that we don't think will impact our goal. We can control them, and so we're going to fix a single set point. The nuisance bucket is where you add factors that you know vary, but are difficult to control. And the main question with these is, do you think they will impact on your response? If you identify that it's something you can't control, but you don't think it's going to have an effect, you wouldn't adapt your experiment design to account for it. If you can measure how a nuisance factor varies during the iterations of experiments, then you can always assess retrospectively if it correlates with the variation in your response and is having an effect. The next two points we will get to in more detail later in the talk. But essentially, if you think your nuisance factor is going to impact your response and you can control it, you use blocking. This essentially splits your rationally designed experiment into blocks by that factor. And this can then be accounted for when modeling your data. An example may be having to run experiments split between two lab scientists. On the other hand, if you can't control the factor, for instance, running the experiments at different times of the day, then you can randomize the order of experiments. Randomization of the experiment run order reduces the chance that you attribute something like warming up of an incubator at the start of the day with the impact of changing, say, substrate concentration. Without randomizing running the experiment, where all high set points for concentration of substrate are run at the beginning of the day and all low set points are run at the end of the day, you may correlate that with the warming up of the incubator. So here are the nuisance factors assigned from our list of factors, and we will talk about blocking and randomization in more depth later. And finally, the experimental factors that are varied systematically using the DOE methodology. These factors must be controllable. In general, if you are screening or exploring, you will likely have many factors with their associated range of set points being set relatively broad. If you know more about the system, you will know the few significant factors that impact the response and will likely be focusing in on the ranges of associated set points to achieve your goal. We will talk about setting the range of factors soon. So here we have defined the factors which are going to be our experimental factors. So the next step is to further classify our experimental factors, giving each a type. This information is then used in our statistical software to design your experiment. The first type we're going to assign to our factors is whether they are numerical. And these are continuous factors like substrate concentration, where within a range, like between 1 and 10, you can have any value between these 2 points. The next assignment are the categorical factors. These are the ones that are split into distinct categories or groups. If we think about media, you may be able to purchase the same media from 3 different suppliers, supplier A, B, and C. And you might think this will impact your response. So you make media supplier a categorical factor for your experiments. An important consideration when thinking about how many runs of an experiment you can perform is that categorical factors tend to increase the number of combinations required to evaluate your biological system. as you require observations of all the other factors for each group of that categorical factor. If possible, try to turn these categorical factors into numerical ones. For example, upon evaluating the media from different suppliers, you see that it's actually the carbon-nitrogen ratio of the media that differs. And so this will become the numerical factor we will include in our experiment. And finally, assigning discrete numeric factors, which are ones that are numbers and have a set amount of levels between two values. An example maybe being a water bath, where you can only change settings from 30 to 31 or 32 degrees. For this particular water bath, we can't set it to 30.2 degrees. So to recap, we have done this classification of the type of factors as this information feeds into our statistical software tool to get started using DOE. I understand it's a step that biologists you may not be too familiar with, but hopefully you'll find easy enough to do. The next step is to assign the range of set points, also known as the factor levels, for each of these experimental factors. To set these range, you should utilize previous data, the literature, or intuition from subject matter experts. The next few slides, I would like to show you the consequence of setting the range of factors at different levels and what we would conclude from the subsequent observations. So continuing our protein expression example, we are showing a graph of the effect of substrate concentration on our measured response of yield. In this example, we are setting the factor range too narrow, focusing on only a small proportion of the entire possible range for substrate concentration. This is what you'd see as the impact of substrate concentration on yield. Here you may conclude that substrate concentration has no impact on yield, and you'd be correct for this range of settings, but you've missed a lot of knowledge about the impact of substrate concentration within your biological system. This example is setting the factor range too broadly. What would this look like in the example? Again, we have missed the true variation on the response of this factor. An additional point to consider is that by setting factors to extremes, you may also risk failure of your entire process. I will talk about pilot studies in a couple of slides' time as an efficient way to broadly assess if the experiment design space is reasonable, answering questions that you may have of whether you've selected appropriate factors and assigned them reasonable ranges. The next example is if we set our range for substrate concentration appropriately. You can see that we can identify the variation in the yield response. Your expertise and that of your colleagues is crucial in setting these ranges appropriately. The statistical software we use for DOEs provide a checkbox to include a center point to your design. Center points are recommended as they can improve your knowledge of the biological system by assessing non-linearity or curvature, which is something that you won't be able to pick up by varying a factor by just 2 levels. Here, we can see the addition of this center point, run, where all experimental factors are set to the midpoint in their defined ranges. There is indeed curvature in the response of yield. Center points can also be replicated during experimentation, and this allows the statistical software to provide an estimate of noise for the biological system, which is then used when modeling the impact of factors on the responses. But again, if you set the range too narrow, even with 3 levels, you won't be able to see the curvature of this response. This is not too bad, as you have identified that substrate concentration is having an impact, and you would likely decide on the next iteration of the experiment to move the levels for substrate concentration to try and explore to see if you can understand more. The green arrows seem like reasonable set points for the next experiment iteration to explore the potential optimum for this factor and further your understanding of its effect on yield. This brings me to an important point that DOE works well when it is conducted as a series of sequential experiments. This lets you focus in on what's important at a minimal resource cost. For example, for a second iteration where we change the set points for substrate concentration, you would also likely drop some of the other experimental variables that showed no impact in the first iteration. You would set these unimportant factors as constants, and this would minimize the amount of runs required to evaluate the important factors, such as substrate concentration, in your second iteration. This is a prompt for me to discuss noise again. It illustrates that if there's a large amount of noise in your measurement, you may not be able to discern the impact of the variable that you are testing. And this can be exacerbated by setting the range for a factor too narrow, as we may not get a large enough signal compared to the noise to detect the effect of said factor. Now I'd like to introduce you to pilot trials for DOEs that help to give confidence in the factors and levels you have chosen. I took this concept from a course I attended at Newcastle University in 2017, and it's helped me during my planning of DOEs to catch things like the addition of a media component that has made all other components come out of solution, something that would have been very bad for my research activities. So some of the advantages of pilot trials are that they allow you to practice your experiment technique, ensuring logistics for execution are smooth. And they also include running center points, so you can estimate noise for the experiment. And with the addition of the most and least forcing conditions, you can assess whether the factors and levels are reasonable and whether you can broadly achieve your targets. So let's take a look at how they're set up. There are 4 runs recommended for a pilot trial. The most forcing one is where, using your subject matter expertise, you run the experiment with all the experimental factors set to the level that you think will increase the response. In this case, giving you the most yield. Then there are the center point runs that are performed in duplicate and represent the middle values in the range for each factor. These center points may also be the set points of your current process. And finally, the least forcing run, where the set points for all factors are set to a level that you think will lead to the yield being the lowest. Once you've defined all these trials, you go into the lab and run the 4 runs, collate the data for the response. Let's now take a look at some possible outcomes and what we may consider if they arise. You can see we have a graph with the 4 runs on the x-axis and the corresponding yields on the y-axis. In this example, there is minimum variation between the center points as compared to the variation between the least and most forcing runs, meaning that we are likely to detect effects at the ranges of factors we have selected. So the noise looks to be okay, and the design space is reasonable, allowing us to see a change in the measured response. Additionally, for this hypothetical experiment, we said we want to exceed a certain yield of protein, as shown by this target line. We can see that this looks achievable with the selection of factors and their ranges that we have chosen. All these observations from this pilot run have given us confidence that we can proceed with the DOE and commit further resources for the experimentation required to further our understanding and attempt to achieve our targets. In this next scenario, we can see that there is too much variation in the center points runs, and therefore the noise may prevent us from discerning the effect of the factors included in the experiment. If this occurs, we may want to invest more time in practicing the technique of the experiment, and this may also include optimizing the assay to measure yield. And finally, in this example, we can see the response hasn't changed much, and therefore we may want to reconsider the range of the set points for the factors we have defined for our DOE. So gaining confidence from the pilot runs, we now have defined our factors, and we have considered the range of the associated set points for each, as shown here. We now need to add this information into our statistical software of choice. We will then be ready to choose a design and for the software to provide us with the list of runs for the experiments to evaluate protein expression. I'm going to highlight two statistical software that provide free trials. This is Design Expert and also Jump. You can download both of these and try them out quite easily. In the following slides, I will show you the steps with examples from both of these softwares to get you to a stage where you're ready to execute your own DOEs in the lab. So we transfer this information from here into the factor table of the statistical software. In this case, I'm showing Jump. For each of the experimental factors, we have transferred their classification of their type, as well as the range of their set points or values. You can see that we have also used the information collated in the Ishikawa diagram to define the response and any associated goals. I hope you've been able to see the advantage of the Ishikawa diagrams for getting you to evaluate your knowledge of the biological system you are researching and helping you to get to a stage where you can define experimental factors and ranges ready to run a DOE. The next step is choosing a design to use in your DOE. And I wanted to remind you that this depends on whether you're exploring or optimizing the system. The other aspect you need to consider when choosing a design is the amount of experimental runs you can perform in total and whether you are constrained to run a certain amount per day, for example, 96. We won't have time to go into this today. We'll be looking at choosing different DOE designs in a future webinar. For the purposes of this webinar, in showing you a pragmatic way to run DOEs, I'm going to talk about two-level fractional factorial designs that align quite well with our protein expression example, as we have many factors that we want to screen, and we're wanting to go from the trivial many to the significant few. I also think fractional factorial designs will correlate quite well with what a biologist will want to do when they use DOE for the first time. I wanted to highlight that if we run the full factorial of protein expression, the protein expression factor space, then all combinations of the factors at their corresponding levels would require us to execute over 8,000 runs. We are unlikely to be able to perform this many runs, and so we will look at the implication of fractional factorial designs for screening. And the one thing to remember when you're new to DOE is that as we reduce the amount of experiment runs to evaluate factors, something which DOE allows us to do with rational, balanced designs, we have to consider aliasing. The alias structure of a fractional factorial experiment determines which effects are confounded with each other, meaning as we reduce the number of runs or observations during the experiment, we start to not know whether the variation in response is due to one effect or another. As in, the model says this is important, but it could be this or this. This table is from Design Expert, and it shows you the different aliasing resolutions of designs for two-level fractional factorials. The resolution depends on the number of factors included and the amount of runs required. To simplify the protein expression example a bit, let's reduce the number of experiment factors to 4. The different types of resolutions are shown here, and you can see for 4 factors, 16 runs are required to assess all factor combinations. This full factorial has no confounding or effects or terms. In other words, you have enough experiment runs to discern the impact of all combinations of factors, including main effects and 2-factor interactions. Let's continue with this 4-factorial example and look at resolution 4 designs. Here, we are constrained to doing 8 experiments. And what we get with resolution 4 designs is the impact we see from our main effects are confounded with some of our 3-level interactions, and that some of our 2-factor interactions are confounded with each other. So this is saying the 2-way interaction AB is confounded with the 2-way interaction of CD. In other words, The two-way interaction of factors substrate concentration and pH are confounded with the two-way interaction of solubility agent and exposure time. You should try to understand this aliasing structure and determine whether it is okay using your subject matter expertise. For example, if an effect is determined from the experiment, then I'm pretty sure it will be the interaction of AB rather than that of CD. And here with resolution 4 designs, some of the main effects are confounded with three-way interactions. In other words, the main effect of substrate concentration is confounded with the three-way interaction of pH, solubility agent, and exposure time. When assessing this using your, you may use your process knowledge and think that three-way interactions are pretty rare. So if I see this aliased effect, I would judge it to be the main effect of A. If during your assessment, these alias terms, you think that you do need to be able to discern the effect, then you have some options. Up front of any experimentation, hopefully you can see from this table that you can either reduce the number of factors you are going to look at or increase the amount of runs you can execute. A third option is known as augmentation, where if when you run this resolution 4 design and an effect that is alias is shown to be significant, you can design a second experiment iteration to look at that specific alias term in order to disentangle their effects. Augmentation again links into the theme that DOE experiments should be performed sequentially, with the benefit being that you minimize the use of resource to get to the knowledge of the system. So that was aliasing. And the next topic is blocking. Here we can see how fractional factorial designs in JUMP are defined to be used for screening. And you will notice that you can specify a block size. Blocking in an experiment is grouping runs by a common factor. And we mentioned that this was a good strategy to deal with certain nuisance factors. In general, blocking is useful to remove known sources of variation, such as operators, materials, or timings. So selection of this fractional factorial here, you can run in a block size of 32. And this is meaning you're splitting these 64 runs into 2 blocks. This may be necessary, for example, if you can only run 32 experiments per day. By blocking runs by a specific nuisance factor, such as the day you run the experiment, you are able to estimate the blocked effect of running the experiment on 2 different days. When it comes to modeling, this estimate is used to reduce noise and improve sensitivity to detect effects of the other experimental factors that you are interested in. Blocking does come at a cost of being able to estimate the effect of some higher order interactions. So we want to evaluate the block design for its aliasing structure and make a judgment call if that's acceptable or not. Blocking does give you the advantage that it allows you to run smaller, distinct blocks of experimental runs. Important if you notice that something went wrong, like a fault with a machine. Alternatively, if you ran a massive all-encompassing experiment, then something like equipment failure, if something like equipment failure occurred, this would mean you'd be wasting a large amount of resource. Using blocking, you're able to rerun that block that failed and evaluate your DOE as intended. Moving on to randomization. Randomization in statistics satisfies the requirement to have independent observations for your experiment. As we mentioned earlier, looking at our 3 buckets of factors, randomization of the experiment run order reduces the chance that you attribute something like warming up of an incubator at the start of the day with the impact of changing a factor under investigation from a high level at the beginning of the day to a low level at the end of the day. The statistical software will randomize the runs for the experiment. Here we can see the randomized run order of an experiment specified in Design Expert. Randomization is good. However, I did want to highlight that in order to pragmatically run experiments, you may decide to run in standard order. You can see here that the set points are no longer random, and you can see the balance of the design with representation of high and low level settings being equal. The setup and execution of the experiments may be quite complex, and this may lead to concerns over user error. So in the past, we have conducted DOE experiments in standard order. Excuse me, where you can load everything at pH 5.5 before running everything at pH 7. And this allowed us to speed up execution and ensure the robustness of our pipetting. Standardizing the run order isn't ideal, but if it allows you to physically execute the DOE, where the alternative is running OFAC experiments, then so be it. And so we've got to the stage of the process where the output of making those selections in the statistical software is that we are given a list of experimental runs to go and execute in the lab. The software is rationally designing the experiment, allowing you to assess the results with statistical rigor, but the output here is just a list of things we have to go and do. Again, I'm not a statistician, and I would not be able to use the DOE methodology were it not for the available statistical software. Just to point out a few features in the table, you can see that the runs are randomized. These are the blocked run conditions. We run these experiments on day 1, for example, and these runs on day 2. This is an example of a center point run within the first block, and you can see the numerical values are set to the midpoint of their range. And the spreadsheet is ready for us to input the measured response for each run once we have completed the experiments. Populated with results, this DOE experiment is then ready to be analyzed in the statistical software. So to bring you back to the DOE process, I have shown you how as a biologist you can take a few extra steps to define things in a way you can then use statistical software to create a DOE experiment. I won't be going into steps 3 or 4 specifically, but I'd like to finish looking at step 5 and taking you through a few things that you should do when coming to use the stats software to analyze and visualize the data from your experiment. A sort of minimal work through to get you started analyzing your own experiments using DOE. The first step was recommended by Jaja in the second webinar of this series, and that is to dive into your data. Eyeball it. There is a huge amount of learnings you can take before looking into the models. Interrogate the raw data like you've always done as a biologist. This is the distribution tool in JMP, and you can see the balance of the design, looking at the count of the high and low set points for each of these experimental factors. These are the measured yields for the experiment. In JMP, there is a thing called dynamic linking of objects, where I can select the highest yields for my experiments and see the set points for them. Here I can see that high temperatures, high inducer concentration, and a media pH of 7 seem to be correlated with high yields. We can also select the low yielding runs of the experiment, and this seems to be correlated with lower temperatures and low inducer concentrations. Interrogate this information. Does it make sense? And if you can remember from my introduction, where I used DOE to evaluate a biological system, I also got confidence in the approach and my execution of the experimentation by seeing that raw data explained what was well understood in the literature. The next step with the data is to assess whether it needs to be transformed. Transformation is a mathematical conversion of the response variable that is applied in the same way across the data set. Transformation of data can be required for subsequent linear regression analysis. This is the yield response shown in JMP. How do we know if or indeed which transformation of the data is required? Well, again, we get help from the statistical software. This is a view of the Box-Cox transformation tool in Design Expert. And you can see it is recommending the transform to apply to our raw data response. Thank you very much, stats program. We then apply the transformation to the response data prior to modeling. And here is the log transform of the raw data. which is a pretty common transform in our experience, but we're not quite sure why though. The next step for the analysis is identifying the important factors that have an impact on the measured response, also known as selecting the terms for the model. We use a combination of the half normal plot and Pareto chart to make a decision of which terms we will add to the model, basically choosing things that are above these lines or away from this line. And as we add the terms to the model, we can assess the impact that selection has on the significance of the model. Here, we've included temperature, inducer concentration, and media pH as terms. The statistics then assesses the contribution of the effects of the remaining factors on the response and tells you, based on the terms you've selected, how significant the model is. Here, it states the model is significant, and there is a tiny chance that this could be due to the noise. So this seems pretty good. But what do we do about the terms that are borderline, the ones that we could accept? Well, the phrase that sticks in my head to describe this, mainly because I didn't know what the word meant before learning about DOE, is you want to be parsimonious when selecting terms for the model. Being parsimonious means you are very unwilling to spend money or use resource. And in this context, it means adding the minimum amount of terms that makes your model useful. This is a graph of the observed yield, the actual measured yield, against the model predicted value of yield. And this looks okay. This is the same actual by predicted graph, but this is an example of where you add all the terms from your experiment. It looks really nice with a perfect correlation of the observed and predicted yields. However, this model is overfitted. You have not been parsimonious, and it is likely that this model is not useful in describing your biological system. After selecting model terms, we then move to the diagnostic section of the stats software. Here, we are using the model platform Diagnostics in JUMP, and we want to assess the data in a few different ways to make sure it's good. The Studentized Residuals allows you to assess the data for outliers. If we identify outliers, we would exclude them from the data set, and this would in turn reduce the amount of observations we have for our experiment. Here, if a data point is outside the red line, we treat it as a probable outlier, and outside the green line, we treat it as a possible outlier. So should we exclude this data point from our analysis or not? It's a good question. This plot of residual by row represents the order the runs were performed in, and it is used to detect patterns over time. You want to have a good random spread of the data above and below the line over time. If you don't, and you see things trending up over time, for example, then maybe there is some systematic bias in your experiment, and this will have an effect on your model. You want to investigate the reasons for this and try to remedy. You can also compare different models using the stats software. For example, evaluating different models using the PRESS statistic. This statistic is an estimate of the prediction error of the model using leave one out cross-validation, where models that have a lower PRESS statistic are favored. Shown is quite a stark comparison of two models, but this statistic may help you if you're trying to evaluate the impact of excluding a borderline outlier, for example. Once you've done these steps, you're ready to visualize the model graphs to gain insight into the impact of the experimental factors on your measured response using these models. You can assess the impacts of each of the factors in turn. Here, we are looking at the impact of the main effect of temperature on the response of yield. Use your expertise to scrutinize the models. Does it make sense that increasing temperature would lead to increasing protein yields? It's recommended to validate your model by running some confirmation experiments. For example, an experiment where factor levels are set to levels that the model suggests give you the best yield of your protein of interest. At this point, you may also want to decide on what the next iteration of your experimentation should look like. Maybe you want to hold the set point of some factors that have been shown to not have any impact on your response. Or in this case, you may want to include a middle point and then set the factor level higher than 37 in order to try and explore the optimum for this factor. Finally, and an assessment that you can't get by doing experimentation using OFAT, is understanding how interactions of factors impact your measured response. Here, the red data is when the inducer concentration is set high as compared to low with the black line. The scale across the x-axis is the temperature set point against the measured response of yield. Changing the temperature when using a low inducer concentration has little effect on the measured response. However, there is an interaction between the temperature and inducer concentration. As we see for high inducer concentrations, increasing the temperature set point results in a greater protein yield. This is really great insight. So the final thing for me to do is to introduce you to the Pcr Simulator, which is a tool that, in combination with a statistical software of choosing, lets you practice how to run DOEs from the comfort of your own home. This is the link where you can find the simulator, and it comprises 12 experiment factors that you can set in this parameters section. So the idea is that you generate a DOE design and then input the experiment set points into these parameters and hit run. The simulator will then give you the response for yield and purity, and you can then add these responses back and analyze them in order to optimize PCR conditions with the goal of maximizing both yield and purity. The program has volume constraints, so you can't add volumes that would cause the Eppendorf to overflow, for example. I want to highlight the PCR simulator as a way to get started with DOE with minimum impact on resource requirement. It's a great training tool. There is an associated paper with this tool where the creators who produced it explain it further. You can link to it from this tool itself. The creators of the tool highlight how navigating even this relatively simple experimental space using intuition alone can be very challenging. This is the performance over time of different students trying to maximize the yield of the PCR reaction and shows their varying levels of success. One of the issues was that students relied on chance and previous experience to set the range of their factor levels, resulting in them only in exploring only a tiny fraction of the design space. So what I'm suggesting is that we use this tool to make our first steps into using DOE, and that for all of us, it can definitely help us practice how we should solve these multi-dimensional, multi-objective problems. So in summary, DOEs and Ishikawa diagrams give us a framework to systematically think about research and experiment on complex biological systems. I hope biologists new to DOE can now appreciate how to get to a stage where they can adapt what they already currently do to make a start with using DOE, using these steps to guide them through the process. And finally, I shared a PCR tool, which is a great training tool that allows you to get started with DOEs with a minimum impact and resource requirements. And with that, I'd like to thank Tom Howard and those at Newcastle University for some great training that stuck with me through the years. And I'd also like to thank my colleagues for sharing my passion for using DOE for biological research. Thank you very much.
Awesome. Thank you very much, Steve, for your presentation. I think it was great to see how you've been able to show DOE through a couple of examples and a use case. And it was really helpful for me to understand, and I'm pretty sure the audience found that really helpful as well. We've got a couple of questions, and I also want to make sure that we answer those questions properly. And therefore, I'm welcoming Dr. Marcus Gaseta and Dr. James Arpino, also known as Jaja, who you've probably known from the previous webinars that we've done. And just to give Steve a breather, I just wanted ask Marcus and Jaja, if you could put yourself in the position of the people in the audience, looking at part 1, part 2, and part 3, what do you think will be the things that they'll take away, and what impact do you hope that they've had?
Well, I mean, what I hope is that we've managed to give a bit of an introduction to why DOE is important, what we can be doing with DOE, and then obviously just a brief introduction into how we might get started with DOE. You know, what we've tried to do is distill our sort of pragmatic experience of running DOEs over many years, you know, from all the way back to when we first started with it, and then having used it for many years since then, to kind of give some kind of pragmatic insight as to the power of what they can do and how you can get started. Yeah, so that's what I'm hoping that we managed to bring across.
Yeah, I'd echo the same and say that, you know, I hope that over the first 2 webinars and Steve's webinar today, that we lowered that perceived barrier of entry to doing DOE. It's really not as difficult as I think, or scary as people first think it might be when they're presented with the concept and the idea, and that it can be a very systematic process, as Steve has highlighted and shown today, and truly, with true clarity. I thought it was absolutely fantastic. Thank you, Steve. Yeah, getting going is really not that difficult, and there are digital tools out there, Steve has shown today, which are a great place to start, to even just play with the concepts of DOE outside of the lab before you step in and apply it to your real biology.
Awesome. Thanks for that. And for the audience, please let us know, chat, comments, the Q&A boxes. Please feel free to express how you've experienced this one, but also the previous 2, and it will be good to have a discussion going on to that. Let's have a look at the question. We've got a lot of questions. I want to make sure that we're able to address that. So let me just go to the first question. Can we get the statistical power of particular interaction in a DOE-based study design? Is that possible?
So it is possible within a decent number of the statistical packages. I certainly know it's possible within JUMP. So this is the idea that if you're looking for a particular interaction when you're setting up a design, I think, if I'm interpreting the question properly, then what kind of signal to noise are you going to need to see in your design in order to actually be able to see that particular interaction? And what lies underneath this is, I think, for some of the more complex interactions, sometimes they can be harder to see than, you know, for the main effects. And yes, absolutely, you can see that kind of power assessment of your design when you're designing things. It's quite an advanced design concept. I mean, certainly what I would recommend is that, you know, people just look to set their factor levels as wisely as possible, as Steve has outlined, and try to do as many runs as you can, whilst, you know, keeping it pragmatic and doable. And then look to, you know, run your experiment and see what you get out of it. A lot of it is just, you know, to take the plunge, have a go with the DOE. In pretty much all our experience, I think, across the company, it's nearly always been less intimidating to run in the first instance and yielded a lot more results than we might have expected, even from relatively simple designs.
Absolutely. Thanks for that, Marcus. That question was by Swapna. I hope Marcus answered that question well. If you still have any questions, please let us know in the chat. But I hope that answered your question. Let's go to the second question. This is, I think, a good one for Jaja. This is around the Synthace platform. Is Synthace platform running JUMP software in the background to perform DOE?
That's a great question. No, currently JUMP or any of the other statistical packages that are on the market and available to use, we don't embed them within the Synthace software platform. We have a file upload integration with those third-party statistical softwares. A lot of these softwares will export a DOE design in a simple tabular format as, let's say, an Excel file or a CSV file that can be uploaded into Synthace. We will then interpret that design file into the liquid handling instructions that you may need to execute that in the lab downstream. But we don't have a direct embedded integration with those third-party statistical softwares at the moment.
I think that also brings flexibility, right? So that means you're not really restricted to a JUMP or design expert or an Excel, as you mentioned.
Yeah, exactly.
there might be a higher level point to make here, just in case people aren't aware, but Synthace isn't itself a platform for designing experiments. It's a platform for executing experiments. So yeah, the design can be done in something like Jump and Design Expert. But as you may have noticed with the experiment that Steve put up for even like 32 runs, it can look really quite complex to run. And yes, you know, obviously you can do that by hand. We've all done it by hand on this panel at one point or another. Yeah, running things with automation gives you a huge amount more power to do these kind of designs. And that's what the Synthace software is primarily there to do.
Thanks, Marcus. This is a question back to Steve. You talked about identifying the right initial factors for DOE. Are there any other tools, perhaps on the Synthace platform, for acquiring the literature or metabolic maps? Is this still part of DOE?
I think this is really echoing what Marcus just said, really. The Synthace is for the execution of DOEs. We don't currently have anything that lets you assess the right initial factors initially in the literature, but it's something that we're really interested in. We want to make the user journey for biologists with DOEs as smooth as possible, and so it's something we're really interested in, and so we do think about, but there's nothing currently in the product that helps us do that. Maybe Jar can add to this.
Yeah, all of these sorts of things about, do we have embedded DOE functionality within the platform? And that goes from, the very upstream parts that Steve was speaking about today, so the Ishikawa plots for being able to do your factor curation at the very beginning, all the way through to creating your design. It's something that we are still learning about what are the core problems that users have to really understand what a solution might look like in the future. But it's something, as Steve said, we're very interested here at Synthace. We want to make it as easy as possible for biologists to be able to do DOE. And if that's something that we can do in the future, I'm certain it will be something that we'll be looking at.
Awesome, thank you. Next question. Do you assess different data transformation before deciding on which to use? If so, what are your deciding factors?
I'll jump on that one really quickly. It's a really great question. I think what you've got to remember, like DOE itself is an iterative process of experimentation. The actual data analysis journey can be iterative as well. So you looking at your raw data off the bat, and depending on the type of modeling you're going to do, so if you're going to do some linear modeling, there are some assumptions around linear modeling that you want for the quality of your model to the residuals of your data points around your model to be normally distributed. And that's the thing that when you're doing transformations of your data, you're trying to get to be normally distributed. But of course, you don't know whether you've got normally distributed data until you fit a model first. So often this iterative process is just try, fit a model, fit several models, look at all of the results from all those models, look at the distribution of the residuals of your data points around those model fits. From that, you will get very strong inference as to what transformations you may need to do to your data to then iteratively fit the next model. That next model you fit might then show outliers where the first model didn't. So there's a bit of an iterative process here. Every time you discard an outlier from your data set, you may want to go back and refit that model, excluding that outlier. So it's not a linear journey, there's an iterative journey, and it I think sometimes sounds like a lot of work. It's not as exciting and it's fun. You go on a journey with your data, a total nerd in me here. You go on a journey with your data, really diving into the depths of it to truly understand it and have the confidence afterwards that the models that you fit are meaningful and true. Yeah. So yeah, it's like I said, it's not linear, it's iterative. But yes, there are mechanisms to be able to help you guide you towards what transformations.
Marcus, I can see you nodding as well. Is there anything you'd like to add to that?
Yeah, I just wanted to add that it's also a process which is always then paying reference to your own subject matter expertise, right? So does the model that pops out make sense? Does it, is this something which is actually giving you more information about what you're looking at? Do the different models that you generated through the different ways that you might approach it, Do they correlate with each other? Do they, you know, are there some things that stick out no matter how you model the data? Because those are likely to be the most important things. And I think sometimes when we're building models, we get a bit obsessed with building like the perfect model, or like trying to squeeze every bit of information we possibly can out of the experiment we just run. We've got to be a bit careful with that, because you can end up overfitting things. You can end up squeezing extra bits in there and going down rabbit holes, when actually you just need to be looking at the main things that are impacting your system and working to iterate on those with a subsequent experiment.
Absolutely. Next question for you, Steve. How did you know which was the center point from the table in the presentation? Was it because you set the conditions, or is there a way to tell from the data?
In the design table, if you look at the values at the center points, they're in between the levels that you've set for that factor. So for that one, I think it was 30 and 37. So I was looking at the split in between, and that was all the way across for every factor for that run. It was at the middle set point for that level. So that's how I could identify it.
Thank you. And another question, is there some sort of simulator around potency determination assay development? Have you come across anything like that? Is that possible?
I haven't seen any simulators to that level of specificity. I think the premise of doing DOE, regardless of the application, is the same. And so taking whether it's assay development out of the picture or process development out of the picture, the steps you go through is the same. And so the simulator that Steve has suggested around PCR is a really great place to start, regardless of whether that's the application you intend to apply it to in the longer term. We have lots of people. We have lots of people who are using Synthace to do assay development DOEs, and we know lots of people outside of Synthace users who are applying DOE to assay development. So it's 100% applicable to that assay space. In terms of simulators, there's nothing that I'm particularly aware of off the top of my head.
Okay, thank you. Any Steve or Marcus, have you come across anything like that? No.
I just wanted to mention that the PCR simulator, the guys who've designed it at Newcastle, they include things like pipetting error. So every time you hit run with the same conditions, you'll get a variance around what you get for yield and purity. So it's like quite a nice way to sort of assess the system. But I don't think there are any other simulators like that out there that I've come across.
Thank you. Next question. Can we use DOE to find unidentified factors? And then in brackets, unknown. And if we can, how to use DOE to discover those unidentified factors?
So this is a great question. The simple answer is no, you can't, because the whole point of DOE is you're systematically varying the factors that you have identified. However, all the noise that you see in a system will be due to some uncontrolled, unidentified factors. And what you can often do by looking at the metadata from around your experiment, maybe looking at the conditions that were run at various different times, you can sometimes get hints to what might be going on in some of that noise. You can look at, say, so if you have randomized the run order and you see some systematic increase, say, in your response over that randomized run order, you know it can't be anything to do with the factors you put in there, but it could be something that's systematically changing over the course of when you ran that experiment. And so that can give you a clue as to what might be going on. But no, there's no kind of systematic way. I kind of like to say DOE is incredibly powerful, but it isn't magic.
It's true. Anything to add to that, Jaja? Or
No. There's nothing to add beyond exactly what Marcus said. Perfect answer.
Good. Let's go into the next question. I know we're already over time. So final question that we've got from the audience, which is around blocking variables such as day of experiment. Are they only possible for Factorial design, or can you also use that for design such as D-optimal? Perhaps Steve, you want to start with that?
I'm not really too sure on this one.
Yeah, I'll speak to this. No, you can still have blocking factors for D-optimal design, so response surface designs. There's no reason why you can't block those designs as well. There become limitations with certain design types, like space filling designs that we've shown previously, where you can block up those designs, but you don't get necessarily the same sort of replication of runs and of factors at specific set points or levels across the different blocks because of just the nature of the space filling designs. So you're more sort of partitioning a design space there, so that the power of the design can be, of a space filling design, for instance, can be heavily influenced by blocking. You can take some big hits from doing that, but for other designs like de-optimal or fractional factorials, where you do get that replication across the blocks, and it's designed into the actual, it's sort of accounted for within the design. There's no, totally fine to have blocking factors in those designs. I think it's safe to say that for any design, if you have multiple blocking variables, it's going to have an impact on the power of that experiment. So you do need to start bumping up the run numbers or dropping the number of factors that you're investigating to satisfy those sort of resolution constraints that Steve was talking about.
Got it. Awesome. That concludes our Q&A session. Marcus, you started it, so I wanted to ask if you could end it as well. Any last or final words that you'd like to share with the audience?
Yeah. So I find it really profoundly exciting, the level of response and the number of people who've joined these webinars. You know, we have been passionate about DOE respectively for a huge cumulative number of years. And a lot of the time we've seen that actually there just hasn't been the interest or knowledge about DOE out there. And to start to see this kind of increase and appetite for learning about these much more powerful experimental techniques is really, really exciting. I think the theme throughout all of this has been, don't be intimidated by it. Yes, it's new, but a lot of it you're already doing anyway. You know, you can just take your experimental design just that one level higher and you'll get disproportionate benefits from doing so. Take the plunge, have a play with the simulator that Steve showed, and then, you know, get into the lab, run your first DOE. I can almost guarantee you won't be disappointed.
Awesome. Thank you for that, Marcus. And with that, we'd like to conclude the webinar. Thanks a lot, Steve, for running us through the last third webinar on DOE, Jaja and Marcus as well. And also thanks for answering all these questions. Most importantly, thank the audience for participating, joining, listening, and sharing any of your questions. If the questions that you've asked we haven't been answered, we'll definitely follow up on that. So we'll be writing a blog in the future, and it will probably be definitely a next webinar where we can discuss this. So definitely follow us on LinkedIn and subscribe to anything that is around with Synthace so you can stay connected. If you've missed the previous webinars, don't worry, we'll send you a link with today's webinar recording as well. And if you have more questions about DOE or how Synthace works with life science R&D organizations, I'll definitely say LinkedIn. You've now seen Marcus, you've seen Steve, you've seen Jaj as well. They're all on LinkedIn. Send them a friend request, ask them any questions, and I'm pretty sure they're happy to chat to you. Another option is definitely to email us at hello@Synthace and or filling up the contact us form on the website. So thank you, everyone, and please enjoy your day and hope to see you again next time.